Assalamualaikum and good day. I'm Ms. Amira binti Muhammad Yusof from Faculty of Mechanical and Automotive Engineering Technology, University Malaysia Pahang. Today I would like to present regarding my research entitled Effect of Laser Power on Temperature Evolution, Brazing Phases and Mechanical Properties of Indirect Laser Brazing.
I will start with the introduction first. So what is actually meant by brazing? Brazing is the joining process that produces coalescence of materials by heating them to the brazing temperature in the presence of filler metal. Or in the simplest way, brazing is the joining process involving two materials that have been joined together using filler metal. This is the general process of brazing, where heat is applied to the base metal and it will instantly melt the filler metal and drawn to the joint. For brazing application, it has been frequently used in automotive, heat exchanger, biomedical, and many more. Brazing have a few types, which is furnace brazing, post brazing, and laser brazing. For this research, we will focus on laser brazing.
Laser brazing is a process in which the heat source is replaced by a laser and allowing for localized heat application. Basically, laser brazing has a few advantages, which is excellent joining surface quality, joining of dissimilar metals, and short processing time. Laser brazing can be divided into two types of technique, which is direct laser brazing, and second one is the indirect laser brazing. Indirect laser brazing is actually involve laser irradiation on top of the base material, and its attempt to create joints where the filler metal is met uniformly while avoiding the heat loss. However, during laser brazing process, many input parameters such as laser power, brazing speed, and many more that determine the joint quality in terms of the mechanical properties and also filler spreadability. In the brazing process, laser power plays a key role because it is influenced the braze joint structure and also temperature profile obtained. Next, problem statement. Joint quality is dependent on the processing parameters such as laser power. However, there are limits to the state of the art laser brazing. Joint quality is directly affected by the laser power as well as the brazing temperature. Brazing temperature is important because it is related to the melting process of filler metal. Overheat in filler metal may result in the reduction of the joint strength. However, too low temperature may cause incomplete melting. In brazing process, the difference of laser power would show the difference in brazing phases, temperature evolution, and mechanical properties. Thus, to achieve a sound braze joint, this parameter need to be studied. For our objective, first is to study the effect of laser power on temperature evolution and brazing phases. Second is to analyze the effect of laser power on mechanical properties. Next, methodology. For material, we use copper rod and copper plate as a base metal and MBF2002 as a filler metal, which is copper-based filler metal. This is the dimension of the brazing sample in T-joint configuration. For temperature measurement, we use infrared thermometer, and for laser brazing, we use laser IPGY at the end machine. With laser power 30 watt, 40 watt, and 50 watt within 60 seconds, and vacuum pressure 400 Pascal. And this is the schematic of laser brazing setup. For test analysis, we test for the shear test and fracture analysis using optical microscope. Next, results and discussion. First, effect of laser power on temperature evolution and brazing phases. This is the temperature profile with different laser power. From here, the temperature evolution can be analyzed by identifying the pattern of each temperature profile. So, the temperature showed a little fluctuation, and it is related with the laser power used and attributable to the jig setup before the brazing process, where there might be a slight moving during the setup. However, it is assumed to be consistent because the pattern shows almost the same for all laser power. By considering the melting point of filler metal, it is melted at the second phase of heating, where complete brazing occurs. So, from the temperature profile here, we can see that as the laser power increased, it will faster the brazing process and the melting duration became short in time. This is the brazing temperature data. So, from the graph here, we can see as the laser power increased, the brazing temperature increased. It is because when increase the laser power, there will be more laser energy absorption, thus the brazing temperature will increase. This is the comparison of brazing phase for high temperature of each laser power. From here, we can see the brazing phase for each laser power. First is the initial heating phase. where heat has to be allowed to dissipate into the base material and maximum heat is transferred to the inner space of the joint. At these phases, the filler metal still doesn't melt and still in the solid state condition. As the laser power increases, the heating rate will decrease because low heating rate will ensure the even temperature distribution on the surface. Second is the melting phase, where temperature rises continuously with time. And at this phase, when increase the laser power, it will be more energy supplied and not consume much time to melt the filler metal. And the melting duration will decrease. And the third one is the second heating phase, where complete brazing occurs. Brazing temperature increase naturally as the laser power increase. This is the schematic diagram that explains why there is a slight up and down in the brazing temperature profile. First is the initial setup, and the second is initial heating, where the filler metal misplaced and slight moving. That is explain why the filler metal still doesn't melt at this phase. Next, the initial melting phase, where a filler metal having a small contact area with the rod and it start to melt. And as the more heat transfer from rod, the filler metal fully contact with the base metal and filler metal will melt and complete brazing occur. Next is the brazing cycle rate average according to the brazing phase. From the graph here, at the 30 watt of laser power, the initial heating rate is low. In comparison, the melting duration high, and vice versa for 50 watt of laser power. It is related to the reaction and diffusion occurs during the laser brazing process. After all, the rate of each brazing phase can vary as the laser power changes. Second is the effect of laser power on mechanical properties. This is for tensile shear strength. From the graph here, we can see the strength varied with the further increase of the laser power. It is clearly seen that the effect of laser power towards the brazing temperature affects the tensile strength. With the optimum brazing temperature, the brazed joint will have a good joint strength, whereas too high brazing temperature will degrade the joint strength. Fracture analysis. The filler metal for all the laser brazed samples are melt and well spread between the joints. Filler spreadability is influenced by the brazing temperature, where optimal brazing temperature results in the better spreadability and joint strength will increase. For conclusion, first, as a result of investigating the effects of power on temperature, evolution and the brazing phase, it was found that as the laser power increased, the brazing temperature increased with the variation of the brazing phase. The temperature evolution can be varied for each laser power used. Second, high tensile shear strength is obtained with the optimal combination of laser brazing condition of a 50 watt of laser power, 400 Pascal vacuum pressure, and 66-second brazing duration. The high temperature will accelerate the heating, which accelerate faster the diffusion elements and reaction at the interface, hence result in the high shear strength. The joint strength is also influenced by the filler spreadability, where the better spreadability is found when the optimum laser power is used. I think that is all from me. Thank you.